So in these NyQuil commercials, usually there's one scene where the person is really sick, and then they take, one dose of the medication, and then they're perfectly fine. And that's not how it works, actually. So if I fall over during my talk, that'll be why. I'll try. Okay, so I'm going to try and state the main theorem nice and early for this reason. So I want to let Z be a projective toric variety. It can be smooth, it can be singular, I don't mind. Projective toric variety. And the space that I'm interested in, there'll be a lot of suppressed discrete data. I'll denote it L naught of Z. So this will be a moduli space of maps, something that might come up when you define Gromov-Witten invariance. So it'll be a moduli space of maps of pairs where I have a smooth curve C and a bunch of marked points, which I'll think about as being a boundary divisor and mapping to Z, boundary of Z. All right? So this is a proper map of pairs. So in particular, I want the complement of the points to go to the interior, to the dense torus, and I want the marked points to go to the boundary. And in the particular context I'm interested in today is when the genus of the curve is 1. So we're talking about elliptic curves. And let's say for the interior, the reason there's a circle on the top there is that I want the curve to be smooth, and then I want to fix the curve class of the image and the contact orders of pi with the toric boundary. Okay, so basically, just that last bit might need some explaining. For every marked point pi, I'm going to tell you which boundary divisor it goes to and fix the contact order at that boundary divisor as well. Okay. Okay, so that's my interior. That's the interior of my moduli space. So theorem. This is still in progress. Maybe it'll be done by the time I leave here. Okay, so there exists a modular compactification, meaning a compactification that's a moduli space of something, V of Z of L naught of Z. That is has a bunch of nice properties. So it has toroidal singularities. So you might want to think about this as being smooth in some category. That category is logarithmic schemes. Okay, so it has toroidal singularities. It's irreducible. It's proper. Okay, sorry. Compactification. So there are natural evaluation and tautological morphisms. So natural morphisms, maybe I'll say EVI from my moduli space V of Z to the target, evaluation along the marked points. That allow me to define Gromov-Witten invariants as intersection numbers on this space. So maybe I'll just say this. So the resulting Gromov-Witten theory, meaning tautological integrals for pullbacks of classes by these EVI maps, is enumerative, meaning the numbers actually count what they're supposed to count. Okay, so they actually count genus 1 curves of fixed degree and fixed contact order in the toric variety. Okay, so that's the main theorem, and I want to tell you about how this is done today. Can I answer any questions about the statement before I carry on? Okay, good. Okay. All right, so maybe just to keep one example in mind. Just think of, you could take P2 with the toric boundary, 3 lines. You could take D to be 3, and then you could take the transverse contact orders to be transverse. So you could consider elliptic curves in P2 with transverse contact with the toric boundary. And then already this moduli space is singular. The conserved space is singular, and there's some content here. Okay.
Do you mean n, the number of points?
No, I don't mean the number of points. I mean the degree, so beta. Thank you. 3 times the classical line. Okay, so let me. So the conserved space, of course, is probably familiar to most people in the audience, but I want to remind you of some of the pathologies that come up in some fairly easy situations. So maybe some motivation. Okay. So the basic object that we're interested in, right, is something like this. So let's simplify further. So this is I'm interested in the moduli space of genus G curves in projective space of fixed degree. Right, so this is the usual conserved space. This is stuff that's familiar to anyone who's ever computed Gromov-Witten invariants. Okay, maybe you want to put mark points there if you'd like. So the first thing to know about this space is that it's non-compact. Right, so if I'm interested in counting curves, I want to do calculus on this space, and so I better compactify. And the choice of compactifications, there are many of them. So one could initially, I think the classical thing that was done is people compactified using the Hilbert scheme. And this is troublesome from the point of view of enumerative geometry. And instead, I think what many of us here like is the conserved space of stable maps. Okay, so I won't define this super rigorously, but maybe I'll put it in a spectrum. So if you think of the Hilbert scheme as sort of living far on the left, right? So the space MGN or maybe MGPRD, that's just generically that's just degree D genus G curves embedded in projective space. And when you want to compactify via some moduli space, you have to decide what are the horrible objects that you're going to allow in the boundary. And when you work with the Hilbert scheme, you basically you force the map to continue to be a closed immersion to be, right? Meaning you want a subscheme, you want a subvariety, but then you let the curve become horrible. Let's see, become arbitrarily bad. And then all the way on the other end is the stable maps compactification, which says that you only allow the mildest possible singularities of the curve itself. So you only allow nodal degenerations of C, but then essentially arbitrary maps. Okay, so it's perfectly fine if your arithmetic genus G curve, if your genus G curve is mapping to projective space by contracting lots of components and multiple covering its image. And that's all completely fine. And then the stability is just saying that, we want this thing to be a reasonably nice space. So that's just a condition on the automorphisms. Okay. So what's the first hint that the conserved space is worth studying and that it might be beautiful? Well, it's beautiful in a very large range of cases. Okay, so this space, M0 n PRD, so just n-pointed rational curves mapping to projective space of fixed degree. This is essentially a smooth manifold. It's stack smooth and it's of expected dimension. Okay, and there's been a great deal of work on understanding the cohomology of this space, the intersection theory on this space, as well as its birational geometry. But then this fails rather quickly. So this maybe the beauty fails quickly. It doesn't age well in Genus, maybe. OK, so I want to focus on two pathologies. So let's do something I think that hopefully seems innocuous. So let's work with a two-dimensional target. Let's replace, OK, not replacing anything here. Let's just blow up P2 at a single point. Right, so this is toric picture as a Hertzsprung surface, first Hertzsprung surface. And here's what I want to do. I want to study the moduli space of genus 0 curves with no marked points in this surface in class 4 times the hyperplane, right? So there's the pullback of the hyperplane class from P2 in this, and essentially quartic curves, and I might want to study quartic curves in this blowup, right? So what does this space look like? Well, it actually it consists of two pieces. Right? So forget smooth; it's not even equidimensional, right? So again, if you're doing calculus, if we're for enumerative geometers and we're doing calculus on this space, then what form am I supposed to integrate on a space that has two different dimensional pieces? So to be precise, this is an 11-dimensional piece. My line is meant to be an 11-dimensional piece, and my plane is supposed to be a 12-dimensional piece. And they do meet. Meet along a divisor in the 12-dimensional piece, I think. Oh, no, they meet along. OK, never mind. I can tell you where they meet. OK, so why can something like this happen? So the expected dimension here, meaning the dimension that you would get from a naive estimate counting parameters, is 11. Right? But there's this 12-dimensional excess boundary divisor that's sitting here. So what does it consist of? So this is a fake calculation, but I think it's illuminating. So you can write 4h. OK, so I have the class of the exceptional divisor here. You can write 4h as 4h minus 3e plus 3e. What did I do? Oh, I did something horrible.
Which one is the exceptional?
Oh. Is it not this one? Oh, it's this one? Yeah, OK. Thank you. Yeah, you're right. Oh, yeah. OK, thanks. OK, so I can think of my class as being 4h minus 3e plus 3e. And if you do this, one thing you might consider is OK, maybe I have a quartic curve in P2. The way you might want to read this is you have a quartic curve in P2 that intersects, that's pulled back from P2, maybe I'll say from P2, that intersects E at 3 points. And then I know what 3E is. This is a triple cover of the exceptional divisor. Okay, so there is a locus of maps consisting of two rational components mapping to my Hertzsprung surface. Oh, got excited there. Okay, so there's a locus of maps like this mapping to my Hertzsprung surface, where the first component is when you blow down to P2 is a quartic curve intersecting this exceptional divisor 3 times, and then my second component triple covers. And because so you can do a dimension estimate to check that this is a 12-dimensional piece, but it's actually quite easy to there's a nice heuristic as to why it's an excess dimensional piece, is because this P1 here, it thinks it lives on a curve even though it actually lives on a surface, right? And so so you're guessing wrong, right? The curve actually lives. It's only mapping to a curve, but it's not moving freely enough, and so your dimension estimates are off in this case by 1. And the thing to really take notice of is that I didn't do that much. Right? I'm still studying genus 0 curves. This is a toric variety. It's not so bad, right? And already you get something that's quite a nasty space. OK, so you might wonder, OK, maybe this is something to do with the target not being projective space. It clearly has something to do with this exceptional divisor here. But you can create pathologies in other ways. Am I still in the right place? Yeah. Okay. So pathology 2. This is actually the case I asked you to keep in mind. So you can take just keep our target as being two-dimensional, but now we can replace having rational curves in our toric varieties with elliptic curves in our toric varieties. And in this case, the space looks okay. So this is M1 bar P3, sorry, P2 3. In this case, the space looks well. The picture is drawn to scale, so it's going to look similar. Okay, so there's a 9-dimensional piece here, right? We all know that there's 9-dimensional moduli for cubic curves in P2, and there's a 10-dimensional boundary divisor. And there's actually another 9-dimensional piece here, which I won't say anything about. So this is irrelevant for now. Okay, so how does this happen? Well, you know what the main 9-dimensional piece is, right? That's just the smooth cubic curves that live inside P2 as plane curves. But here, what you can do, well, okay, so I'm gonna mix my metaphors if that's okay. Okay. So that's supposed to be a P1 glued to an elliptic curve. So half the picture is real and half the picture is complex. But nonetheless, I can map this to P2. And okay, so what can I do here? I can contract the elliptic curve. Right? That's allowed. That's something that I can do in my space of stable maps. I can contract this gadget. And for P1 mapping to P2, I need it to be a cubic, so I'll let it be a cubic. So this is a rational cubic in P2. Right? And genus 0 curve in P2 embedded as a nodal cubic curve. But now to get the genus to be 1, I've attached this genus 1 piece, and I just contract it. Right? And again, what's happening is that this genus 1 curve, it lives there, but it thinks it lives in a point. Right? It's actually mapping to a surface, but it thinks it lives in a point. So there's no restriction on the complex structure of this elliptic curve coming from the ambient space. And for this reason, when you do your deformation calculations, you just get the wrong dimension. Okay? So now you can imagine the setting that I want to work in is to work with arbitrary toric varieties in genus 1. So I'm going to get some funny cocktail of these two pathologies, pathological cocktail of pathologies. Okay? All right. Okay, so how do we get over this? Okay, so the inspiration to I should say I should have said this earlier. So I think the main connection to mirror symmetry here comes from the fact that so in 2006, so Vakil and Zinger, they gave a really nice desingularization. So they desingularized M1 bar, M1n bar PRD explicitly. And this is one of the main technical inputs into Zinger's proof of the genus 1 BCOV predictions. Okay. But basically what I want is a version of this for pairs, a version of this with a more general target and where I allow things like non-transverse contact orders. Okay, so.
Sorry, is there a name for the desingularization that they use? Is there a word for the desingularization that they use in that case?
A word for it? Oh, no, it's not. OK, so this is a good question. So one thing one bonus that this result seems to be giving us is this is not a moduli space. So this is work in progress. So I don't want to claim too much, but it seems as if one thing we'll get out of this is a modular interpretation for their desingularization. No. So what they say is, OK, take your singular moduli space, and here's an explicit collection of loci that I'll prescribe combinatorially, and just blow up these loci in this order. And what you get at the end of the day is somehow miraculously smooth.
Oh, they have also this contact condition or not?
No, no contact condition. This is ordinary concavat space. Sorry, I'm trying to keep the M for the concavat space and the L for the. Okay, so there's no contact condition here, but we can handle that now. Okay, so how to solve pathologies, or these pathologies? I don't want to claim too much. So the main input comes from logarithmic and tropical geometry. So it seems to be the main new tools here. Let's see. Okay, good. It's always good to know when inventors of fields are sitting in your audience, but I don't think Bernd Siebert is in the audience right now, so it's okay. Okay, so what's the idea? So the idea is basically to study a moduli problem for pairs. And I already set this up for you. So rather than thinking, a toric variety naturally wants to be thought of as being a pair of, it's in the interior of the torus together with its boundary. And so maybe that just should be your starting point. Right? So I have a bunch of marked points here, and I want to map to some toric variety, and I want to prescribe the contact orders of these points with the toric boundary. Okay, so once you study the, okay, so you've set up a problem like this. So how do you compactify it? Right, so this is clearly okay, let's just convince ourselves that this is not a proper moduli problem, right? For instance, a thing that I could ask here is a tangency of a curve to a boundary divisor at a fixed point. Well, what happens when this curve falls into the boundary? Right? What is it if I have a component that carries this marked point, let's say P1, and it actually falls into the boundary divisor? I don't know what it means to be tangent anymore. Right? So there's some extra structure that needs to be added on to make sense of that. There's lots of ways to do this. So in the case in the case where the boundary divisor is just a single smooth divisor, this has been known for some time by work of many people in algebraic geometry by Jun Lee. But toric varieties boundaries are unions of such things, and they meet and they're singular. So something else is needed. So the compactification of this moduli problem so this is answered by logarithmic geometry. So this is Abramovich, Chile Chen, and then independently Gross and Siebert. Okay, so generally so there might be some percentage of you that knows log structures in the audience. If so, great. I'm going to sidestep this completely. By giving you a fake definition. Okay, so what's the point? So ACGS, they construct this proper moduli space L of Z that I want. This is called the space of logarithmic stable maps. Okay, so I want to tell you what a C-valued point. Okay, so I want to tell you. I will tell you what does a point in this moduli space parameterize in a sort of not so standard way. Okay, so to do that, I need to tell you a little bit of tropical language. Okay, so the target of my tropicalization, will just be a fan, which I'll think of as the tropicalization of my toric variety. So this is abstractly, this is just some vector space with a fan structure and a piecewise linear structure, and a tropical stable map. This is just going to be a piecewise linear map from a graph to Rn. that is balanced. It's piecewise linear and balanced. So balanced is a zero tension condition. It just means that, so I have a piecewise linear map from a graph into something, into Rn. At every point, I can calculate directional derivatives, and I want the sum of the directional derivatives in all directions to sum to 0. It's just a zero tension condition. Right, so a picture to keep in mind is something like this. Okay, it's not terribly important exactly what they are, but they're graphs together with a map to some vector space. Right? Some piecewise linear version of the moduli problem we're already interested in. And there's some discrete data here. Okay, so there's a well-defined notion of the genus of one of these tropical curves that's going to correspond to the genus of the moduli problem I set up on the classical side. And okay, I'm happy with that. Okay, so just as one can put stable maps in families, one can put tropical stable maps in families as well. So for fixed combinatorial data, meaning fix the underlying graph and the edge directions, the asymptotic edge directions, there is a moduli cone of tropical curves. Okay, so something like this. Okay, so there's some cone whose edge lengths parameterize, whose entry, the coordinates of this cone parameterize edge. You should think of them as parameterizing edge lengths of the tropical curve. And as I move in this cone, I get a piecewise linear variation of a family of these maps. Okay, so maybe there's some universal, some graph here, and a map to sigma. Okay, sigma is the fan of my toric variety, if I didn't say that. Okay, I'm going to pause here. Is this OK for a working definition? Okay. All right. Sorry?
What happens with the vertex of your cone? You see the directions at infinity?
Yeah, I only see the directions at infinity. So at the vertex of my cone corresponds to the graph that has a single vertex and a bunch of unbounded edges, and the unbounded edges go to infinity in the directions that my contact order prescribes. Okay. 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 So why do I need this? There's enough information in the contact orders to specify what?
A unique point at the origin of the cone?
Yeah, that's right. So the contact order, okay, so one way to phrase, the cleanest way to define a contact order is just that for every marked point, you get a lattice point of your fan. And so if I have as many unbounded edges in my graph as marked points, and I have a lattice point for each one of them, I just move in that direction. Yeah, so okay. So now a c-valued point of L of z, just a single point of L of z, I want you to think about as two pieces of data. So the first piece of data that it gives you is an ordinary stable map. So a nodal curve C with some marked points P1 through Pn mapping to Z. Okay, so this is just an ordinary stable map. And the second piece of data that it gives you is completely combinatorial. Right? So this is, what you get is a cone of tropical stable maps. Okay, so basically, so that's right. Okay, so a c-valued point gives me one classical stable map and an entire cone, an entire family of tropical objects, an entire family of piecewise linear objects. So it's some hybrid thing. And then there's compatibility conditions between these.
And it's homological. It's all the guys of a certain combinatorial type.
That's right. It's the maximum cone of that combinatorial type. Right? So compatibility between 1 and 2. So I'll say this in words. OK.
I don't even know. What's the dimension of your space in the end? Is it actually n?
Is the dimension of
The thing you're going to build your L.
yeah, so it's k. OK, so log k is trivial, and so it's just a number of points. Yep. Yep. So it's roughly equal to the degree, or something like the degree, like 3 times the degree, n plus 1 times the degree in the P2 case. Right. Yeah. Yeah. So in genus 0, this is going to give you something that's the modulus of the P1 times the dimension of your space, and in the genus 1 case, you'll just get something that's the number of points on the P1 on the elliptic curve. Yep. Okay. Okay. So there's a compatibility between 1 and 2. So if I hand you a classical stable map, can you somehow predict that the combinatorics that should come out of it? Okay. So you can. So I'll just say a couple of words about this. Okay. So let me give this a name. So there's an entire family of these. So I want gamma to be the dual graph of C, right? So C is a nodal curve, so I can form a graph by taking one vertex for each of its components and an edge for every intersection of the components. And every time I have a marked point, I put on an infinite leg. So maybe if this is my nodal curve, then my graph probably looks something like this. Okay. And then there's a compatibility on the strata. So a vertex, right? So the vertices are in bijection with components of my curve. So a vertex maps to a cone, sigma in sigma, if and only if the Cj maps to the corresponding stratum.
Is it easy to see these n? Is it like the lengths of the central loop? Or
Sorry?
I was wondering if it's easy to see in the tropical picture these n parameters.
Yeah. It is. So you can by Euler characteristics. So you just So if you know the number of unbounded edges and you know the rest of the thing is trivalent, then you know the genus is the first Betti number is 1 and you know n, and so it's easy. You can calculate the number of, it's some graph theory thing. It's like an easy fact.
I was just wondering, there are n segments, it looks like, in the center.
Yeah, and those two numbers will usually be the same, I think. Yeah. So yeah, that is the n in this case. Yeah. Okay, so so I have a stratification of my toric variety into these pieces in bijection with the cones of this fan, and I want a vertex to, in my tropical picture, I want a vertex to map to a cone precisely when the corresponding component that it's dual to maps into that stratum. Okay, so there's some compatibility. You don't need to digest exactly what this means, but okay, maybe you do. Who knows?
So can you, is it okay if, like, you show an example where the order of contact with one of those boundary divisors gives us a point inside that cone or something?
No, it's not going to be a point. It's going to give you the entire cone. Okay, so this is a cone. Okay, so let me give you an analogy. So if I give you a toric variety and I give you a complex valued point of it, right? If I give you a C-valued point of a toric variety, then you really have two pieces of information immediately, right? You have the stratum that point lies in, and you have the point itself. Right? And sure, you might think that that's somehow implicit, but the second one remembers the toric structure, right? So you can remember the cone dual to the stratum which your point goes to, and that's exactly what I'm saying here. Right? So this is just, that's where the combinatorial data comes from. Okay. Right, so the thing to keep in mind is just that it's some sort of hybrid space that has both the classical ordinary stable maps theory and this tropical theory. Okay. All right. Where do I want to go from here? so I wanted. So how singular are these things? Well, I'll just say L of z satisfies, as I change the numerical invariance, L of z satisfies Mignoff universality. So this is sometimes referred to as Murphy's law. So if you've never seen a result like this before, just think that the local geometry of these moduli spaces is basically unboundedly complicated. Okay? So any singularity you can write down over the integers will appear on one of these moduli spaces. And so in general, you don't expect to be able to desingularize all of them, in particular because if you could write down a series of steps that would desingularize them, that would give you an algorithm for resolution of singularities. So this is meant, you expect this to be a hard problem. OK, but in Genus 1, it seems to be that we can do something. So I want to tell you another problem that seems to be quite hard, that has been bugging tropical geometers, including myself, for some time. And it's the problem of tropical realizability, or the inverse, the tropical inverse problem, if you like. So the basic question is this. OK, so how do tropical curves arise? Right, so if I give you a piecewise linear balanced map from a graph into Rn, right, something like the picture that I drew, how can such a thing arise? How does it relate to geometry? So let's remind ourselves of this. Well, the basic setup usually is that you start off with some. OK, so firstly you work over some very large field. OK, so something like generalized power series in one variable with a real exponent, and that admits a evaluation map to the real numbers, at least from the non-zero piece. OK. And what you do is you just take a nice smooth algebraic curve in here, and then you follow what happens to it under the coordinate-wise valuation map. Underline. OK. So maybe I can be more friendly. OK. Right. And it's a fact that as this torus is kind of fibering over this real vector space, the curve in some natural way fibers over a piecewise linear object, which is this graph. So if you like Tony's talk, and this is the language I prefer to work in some non-Archimedean world, this is honestly what I said. Okay, so there's a continuous deformation retraction from an analytic space associated to this curve onto some skeleton. And then this is the easiest SYZ fibration in the world. So torus mapping onto a vector space, right? Just by valuation. OK, so this is one way in which it can arise. OK, so this is one way in which. OK, so this is a tropical curve, a tropical stable map, the way I've been calling it. But then what about the inverse problem, right? So if I give you a balanced tropical curve, can you come up with an algebraic curve and a map to a torus over some non-Archimedean field like this that produces that? The answer is that it's hard. So when does such a tropical stable map arise as such? In the fashion above. Well, in genus 0, meaning first Betti number of the graph is 0, there are no obstructions. Okay, so if what you have is a tree in a vector space embedded in some piecewise linear fashion, then there's absolutely no obstructions, and every graph will arise in this as a P1 It's a smooth P1 mapping in a nice way to a torus that you then take coordinate-wise valuation of, and you get the object that you want. Okay, so this is written down by Nishino and Siebert in 2006. So sort of the first real extension of Michalkin's tropical enumerative results to higher dimensions. Okay, and then I'll leave this one blank for a moment. So when the genus gets arbitrarily large, this is also a problem that satisfies Minyoff universality. So there's a version of this due to myself, and also a version due to Dustin Cartwright in a related setting. So meaning, for very, very high genus algebraic curves, or for very, very high genus tropical curves, embedded in some piecewise linear fashion in a vector space, along the way to figuring out whether or not you'll be able to realize that through algebraic geometry, you're going to have to solve an arbitrary Diophantine polynomial equation. That's the content of the statement. Okay, it's just okay. It exhibits the same realizability properties as matroid realizability, if that's another context you've seen this in. Okay. Of course, in genus 1, Spire gave us essentially the complete answer, and then while I was trying to use this, I finished up the cases that he left out. So in genus 1, there's an explicit piecewise linear condition. So in genus 1, the answer is not always, and it's not impossible, and so there's something that you can do. And the whole motivation for this project was okay, Vakil and Zinger, they give us this desingularization of the space of stable maps in genus 1, and then somehow coincidentally, roughly at the same time, Spire proved that genus 1 tropical curves were realizable in this particular condition, and the goal was just to understand that these two results are related in any fashion. And if you dig into this long enough, you'll see why you might think they should be. It's not such a crazy thing. But the content of this theorem that I stated earlier is really exploiting that. So let me give you a flavor of what this condition looks like, because I have some time. Okay. So this is a perfectly fine tropical curve. It's genus 1. It has one cycle in it. And you can map it into R2 in the following way. So it's piecewise linear in the sense that it looks piecewise linear. And then what I want is for this map to flatten the loop. Okay, so I want this. So I've drawn it. Okay, in real life, you can't actually see that there are two things here. Okay, so these actually lie in a line. Okay, this is some piecewise. Okay, this is a piecewise linear map from a graph to R2. Right? There's nothing fancy going on here. But just like I was mentioning earlier, there's a piece of this curve. There's a genus 1 piece of this curve that thinks it lies in a line, even though it ought to live in some two-dimensional vector space. And so you have a deformation space combinatorially that's larger than expected. Okay, so the condition that Spire noticed is that gamma to R2, meaning this thing here, is realizable if and only if L1 equals L2. Okay, so there's some explicit piecewise linear condition on the edge lengths. So if these two edge lengths are not equal to each other, then there's no algebraic curve that this comes from. And if they are equal to each other, then there is some algebraic curve that it comes from. Okay?
Because like two boundary divisors are linearly equivalent, or is that the contact?
No. So no, it's not quite that. Yeah, I don't know of a simple way to write this down. This is just what comes out of the obstruction theory calculations. So very briefly, I can tell you. So this is encoding some singular algebraic curve mapping to this toric variety, to some toric variety, and that singular algebraic curve has a deformation space that's singular. That's a singular point of the moduli space just by virtue of the fact that of what I told you. This curve is moving in a moduli space that's higher dimensional than it looks. And so perfect obstruction theories essentially are fancy ways of cutting out a moduli space from inside its own tangent space. So you can, in principle, in explicit cases, you can write down what those equations are. And then when you write down those equations, you notice that the sort of deformation parameter on the classical side corresponding to this and the one corresponding to this have to be equal. So this is just some calculation that you need to do, and this is what comes out. So this is not how Spire proved it, but I think that's how we understand it now. Okay. All right. Okay, so let me tell you how to desingularize this space. So the first question is, so I'll phrase it vaguely. How is gamma to R2 in the non-realizable case related to geometry? Right, so if I give you one of these things, let's say this map where L1 and L2 are not equal to each other, is that just some fantasy cooked up by polyhedral geometry, or does it have anything to do with algebraic geometry? So there's an answer to this. So this was inspired by work of Abramovich and Weiss. And then I kind of wrote down the details in my thesis. Okay. Okay. All right, maybe I'll phrase it this way. So given any toric variety Z, there's an interesting stack that one can construct, which is just Z mod the dense torus. Right? So this is it's a funny object. It has finitely many points. And so in this audience, what I would say is so one way we construct the map from Z to its moment polytope is by quotienting by the compact S1 to the n inside of it. So I want to do some algebraic version of that. In algebraic geometry, I don't have S1 to the n, and so instead I'll use the whole thing. But then if I take an appropriate Berkovich analytification of this, it was noticed by Martin Ulrich, Z top, it was noticed by Martin Ulrich that the map, sorry, this is Ulrich's theorem, it was noticed that the map from the analytification to this sort of canonical map to the stack quotient is exactly tropicalization. So it's just another word for what we had been calling tropicalization all along. Right? So this is some stack theoretic enhancement of what I wrote down earlier. And basically, the way I told you to realize to realize tropical curves earlier was to take an analytic curve mapping into this analytification of a toric variety and then tropicalize. Okay, so maybe I'll say it like this. And then what I'm also saying is that this is some Z here is my toric variety. Okay. And what I'm saying is that there's actually some secret algebraic stack hiding here that is recovering all the information of the tropicalization. And so the answer is that maybe you can't always map through Z to your tropicalization, but you can always map directly to this stack. Okay. So I'll just phrase that a slightly different way. So the space. Yeah, it's just retraction to the skeleton. So quotienting by the so you should really think about this as after analytification. Okay, I'm leaving something out, but after analytification, the Z mod T just looks like modding out by S1 to the n on a compact toric variety, when you can make sense of S1 to the n. But we can't do that in algebraic geometry, so we go through this. Okay, so this is almost equivalent to the statement that if I study logarithmic stable maps, just like what I did earlier, if I study logarithmic stable maps not to Z, but to Z mod T, which is this funny zero-dimensional stack, then I get something that's log smooth. Okay, so I get something that's toroidal, okay? Maybe I even finished a couple of minutes early.
Stack up that you don't actually always have a map from Cn to Zn because it could go into some kind of.
That's right. So, well, no. So, okay, so basically, I'm rephrasing the abstraction of lifting. Okay, so there's always, given a tropical curve, there's always a map. There is always an analytic curve, and there's always a map to this analytic stack. The question is, does it filter through this guy?
So you're saying that this tropical realizability is true if you take it to mean.
If you take it to mean, that's right. So tropical realizability is always true, provided you're willing to say, OK, I'm mapping to this toric stack instead of this toric variety. And that's almost equivalent to the statement that the moduli space of logarithmic stable maps to Z mod t, to this Artin stack, is actually toroidal. It's as smooth as you're willing to get in this world. OK? OK, so what is, OK, so toroidal embeddings, for now, just think of these. If you've seen them before, great. But if not, just think of them as toric varieties. They generalize toric varieties. OK, so, this is not specific to genus 1, sorry. What I'm about to say is. So I'm going to construct this desingularization for you. OK, so now there's a lot of pretty coincidences that happen now, so I'll try and say them clearly. OK, so what have we set up for ourselves? We have a singular moduli space, L of Z. This is genus 1 now. Okay, so genus 1. You have some singular moduli space, but it maps to a smooth thing, or almost smooth thing. Okay, it should be clear that there's a map, right? So I told you that L of Z is two different pieces of data, an ordinary stable map and a tropical stable map, or family of tropical stable maps. So the ordinary stable map I can just compose with the quotient to the stack to get a map to Z mod t, that's fine. And then what about the tropical stable map? Well, the tropicalization of Z and the tropicalization of the stack are the same thing, and so nothing changes there. Okay, so there is a naive and obvious map in this direction. And this is log smooth. So being log smooth is the same thing as that word I wrote above, toroidal. Okay, so when I said, okay, so now I'm really going to cheat. So when you have a toric variety, there's a fan associated with it that we all know and love, right? And so this being log smooth, this being toroidal, there should be some fan associated to it as well. So you can ask, what is that fan? Okay, so maybe L of fan of, oh gosh, this is going to get gnarly. Okay, so there's some fan. And you can ask, what is this fan? Okay. So the fan, this is the moduli space of tropical curves, of all tropical curves, meaning all of the cones that would have shown up in that construction I mentioned to you earlier, you can stick them together to form a fan, and that's what this fan is. Okay, so this singular moduli space is mapping to something log smooth. This log smooth thing is, okay, this toric, almost toric thing, in some Stacky sense, it has some fan associated with it, and this fan has a modular meaning. It has an interpretation as a moduli space. Okay, so this is a beautiful coincidence. It's really not a coincidence, but at first maybe. But the key here is that it's the moduli space of all tropical curves, including these garbage ones over here that I don't like. Right? So including the ones that are not realizable, that have nothing to do with algebraic geometry. And so what can you do? Well, you can try and find an interesting subcomplex here. Right? You can try and subdivide your fan and then find an interesting subcomplex that only consists of the realizable ones. So let me do an example. Right? So there's three dimensions of moduli here, right? 1, these two lengths have to be the same, and 3, right? So 1, 2, and 3. So it's a cone over this triangle. And if I want L1 to be equal to L2, that's my realizability condition. That's a face. After subdivision, that's a face. Right? So there's a 2-dimensional cone sitting in here. So I can make a polyhedral subdivision of this and then extract the locus of realizable tropical curves. So there is an explicit condition. I'm not going to tell you what it is, but you can do it in genus 1. It's quite easy. Okay, but we know what morphisms of fans are in the toric world, right? So if I subdivide a fan and then extract a subcomplex, that's saying blow up and do some proper transform. So this produces some gadget.
By the way, is this thing on the lower right, is if you just took, and maybe I found it, if you just modulate tropical curves, is that thing itself a fan?
Yeah, it's a fan in the weak sense, and it's piecewise linear. There's no ambient vector space.
Oh,
Yeah. Yeah, it's a fan like in the sense of a YD fan. It's a fan. Yeah. OK. But nonetheless, the identification of this purely combinatorial realizability condition produces some, OK, now stack, but whatever, some blow up and piece of this stack that you're interested in. And if you think about, OK, so this is also toroidal. This is also log smooth. And its fan is the locus of all realizable tropical curves. OK, so now you kind of see the connection between these two things. So you can form a fiber product here. Right? You can pick out sort of the locus of things here that, right, OK. Form the fiber product. And then the theorem is that V of z desingularizes the main component of the Abramovich-Chen-Gross-Siebert space. This thing I wrote down earlier. All right, maybe we should go get some tea. I'll stop there.